All right, get ready because today we're going deep on something pretty unexpected.
Dripping faucets?
Yeah, dripping
You
faucet.
heard that right.
I know. It sounds a little, well, boring.
Mundane
Yeah, mundane. But trust me on this one. It's going to be good. We're talking about this 1984 research paper.
by Robert Shaw.
Right, Robert Shaw. And it's called
The dripping faucet as a model chaotic system.
Catchy. Right. But seriously, this paper is blowing my mind. It turns out even a regular dripping faucet can teach us a ton about, well,
About predictability and chaos and even...
the limits of knowledge.
Yeah, how much can we actually know about anything? Even something simple.
Right. It's like those everyday things we see all the time but never really think about.
Exactly. Like we've all seen a leaky faucet.
1,000 times.
But we probably haven't thought about all the hidden complexity going on there.
Definitely not. So what was Shaw actually trying to figure out with this dripping faucet experiment?
He was looking at this big question. Can we really predict anything? Even something as basic as when the next drop is going to fall from a leaky faucet? Like, you'd think that if we knew all the laws of
You'd be able to predict anything perfectly, right?
Exactly. But Shaw's research, it's hinting that it's not that simple. He very carefully measured the time between drops from a faucet with a controlled flow rate. And what he found was that even super tiny, almost impossible to notice, differences in how things start off, like the exact shape of a water droplet before it falls.
Uh-oh. So you're saying my morning coffee could be totally different just because I stirred it a little differently?
Think of it like, the butterfly effect in action.
Okay.
A tiny change in one part of the system can have this ripple effect, making it really hard to make predictions way out in the future.
Whoa. And that's where deterministic chaos comes in, right?
You got it.
But wait, deterministic but unpredictable. How did that work?
Yeah, it is a little bit counterintuitive. I know deterministic means that the system follows specific laws of physics, but those tiny starting differences can make the system act in ways that are impossible to predict over time. It's like trying to predict where a leaf is going to land.
When it's windy.
Yeah, in a crazy wind it follows physics, sure, but good luck figuring that out.
So even though the dripping faucet is following the laws of physics, those tiny variations mess up our predictions.
Precisely. Now, to look at this, Shaw didn't try to deal with all the super complicated physics of water itself. Instead, he did something really clever. He focused on when those drops happened.
So instead of studying the water, he studied the rhythm of the drips.
Exactly. He treated the dripping faucet like it was some black box that just made a series of numbers those times between drops without getting lost in all the complicated fluid dynamics.
That's smart. But how do you even analyze those patterns? It's not like you can just look at a list of numbers and be like, oh, there's chaos.
You need a way to see the patterns, and that's where tools like time series and time delay plots come in.
Okay.
These are basically graphs that plot the drop intervals against each other, showing you places where it might be possible to predict what's next.
So it's like looking for a hidden code in the timing of those drips.
Yeah, kind of. But then Shaw throws in this whole other thing. He uses information theory, which you usually think of with communication, to try to understand these patterns.
And that's where things get really wild. So break it down for me.
Okay, so information theory gives us a way to understand not just communication, but also how systems behave and how predictable they are. Think of it like this. Information is how much we know about a system, and entropy is how fast that system forgets what it did before.
So high entropy means it's harder to predict the next drip.
Yeah, because it's losing its memory quickly. But here's a tricky thing. Even those perfectly timed periodic drips, they don't actually have much information.
Wait, what? Those predictable ones have low information? I thought predictable things were like full of information.
It goes back to those tiny changes we were talking about. Even perfectly periodic drips, they still have really small changes. And those changes, they're basically just random noise. Like, imagine a clock that ticks at a steady pace, but there's this little jitter in each tick.
Okay, I get that.
That jitter, that's random noise. You can't use it to say what the next tick will be like.
So even though the overall pattern's predictable, those tiny variations are completely random.
Exactly. And that's where the difference between deterministic chaos and random noise is super important. In chaotic systems, there's like a hidden order, a pattern underneath all the randomness.
But with noise, it's just random, random, random.
Yep. No pattern, no information you can use.
So it's like the difference between a secret code and just static on a radio. Okay, I think I'm starting to get this. But how did Shaw actually measure how predictable the dripping was?
That's where he uses this idea of stored information. It basically tells you how much knowing what happened in the past helps you figure out what will happen in the future.
That's sense.
And not surprisingly, the different dripping patterns Shaw saw, like periodic, period doubling, and chaotic, they all have different amounts of this stored information.
So more stored information means we can predict it better.
You got it. And how fast that predictability disappears, that's measured by the entropy.
So high entropy, less predictability.
Exactly. It makes you wonder about those big systems we deal with all the time, right? Like the weather,
Yeah.
the economy,
Huh?
even the way we act. Are we just chasing this impossible dream of perfect predictions when even something as simple as a dripping faucet is so unpredictable?
It's kind of mind-blowing when you put it that way. So is Shaw saying we can never predict anything, right?
Not exactly, but his research is saying there are limits to how well we can see the future, even in things that follow laws of physics. And those limits, they're tied to information itself,
Okay.
how it moves through these systems. And to really get this idea of information and prediction, Shaw actually brought up a quote by Stephen Hawking.
Okay, now that's a name I know. What did Hawking have to say about dripping faucets?
Well, not faucets specifically, but Hawking was thinking about if we're getting close to understanding all the basic laws of
Like
physics.
having a theory of everything.
Right, and Shaw was basically saying, hold on, not so fast.
I like that using this simple dripping faucet as like the perfect counterexample.
Exactly. Even if we completely understood the laws that make water molecules do their thing, predicting a dripping faucet over a long time would still be super hard. It all goes back to that sensitivity to initial conditions. Those little uncertainties can just snowball.
So understanding all the little parts doesn't mean we understand the whole thing. It's like saying, because I know everything about bricks, I automatically know everything about building a cathedral.
That's a great way to put it. Systems can have these emergent behaviors, things that go way beyond just adding up all the parts. Think about a flock of birds.
Okay.
Just knowing how each bird flies wouldn't let you predict how the whole flock will move, right?
Makes sense. This is making me rethink how much we can actually know about anything. If we can't even predict a single drip perfectly, what does that mean for things like the stock market or climate change?
It's a big question, and Shaw's work is saying we might need to change how we think. Instead of always going for perfect predictions, maybe we should focus on understanding the limits of prediction. Figuring out the uncertainty that's just built into complex systems.
So it's not just about having better computers or more data. It's deeper than that.
Exactly. The way chaotic systems work, with how sensitive they are to those tiny starting differences, means that even small gaps in what we know can make things unpredictable on a big scale. Now, to actually study this, Shaw had to analyze all the data from his dripping faucet experiments. He used things called histograms to show the probability distributions of the different drop intervals.
Okay, histograms, remind me what those are again?
Imagine a bar graph, okay, showing how often different drop intervals happen.
Gotcha.
By looking at these histograms, he could measure how much information was in the system and how it changed.
So let's talk about some of the specific dripping patterns he found. What did they tell us about predictability?
One thing he found was that when the drops were perfectly periodic, like clockwork, there was actually very little information.
Wait, those super predictable drips had hardly any information. I thought predictable meant full of information. How does that even work?
It's those tiny changes again. Even the periodic drops still had small variations, and those variations were basically random noise. Remember the clock with the jittery ticks?
Right, yeah.
Same thing.
So even though the overall pattern was predictable, those tiny variations messed everything up.
Exactly. And here, it's so important to know the difference between deterministic chaos and just randomness. In chaos, there's a pattern, a hidden order behind the randomness.
Okay,
But with pure randomness, there's no pattern at all, no information.
okay, that makes sense. What about those more complex patterns? What about the period doubling where the drops start pairing up?
That's where it gets even more interesting. Shaw found that when the drops were doing that period doubling thing, there was actually a decent amount of information stored in the system. If you knew the timing of one drop, you had a good chance of predicting the timing of the next one in the pair.
So there's a pattern to the chaos. It's not just random.
Right, and the information stored was about 1 bit per drop.
Okay,
1 bit in information theory means that knowing one drop cuts the uncertainty about the next one in half.
interesting. So it seems like the more complex the pattern, the more information is stored. What happens when the dripping becomes completely chaotic? No clear patterns at all.
Well, things get really messy. The information stored in the chaotic regime, it depends on the specific pattern and how much noise there is.
So it's way harder to know how unpredictable it is.
Exactly. But Shaw found some clever ways to figure it out. He was basically measuring how fast our ability to predict future drops breaks down as time goes on. And he found that even in the chaotic regimes, there was still some predictability in the short term.
So it's like saying, I can't tell you exactly what this faucet will do in an hour, but I can tell you what it'll do in the next few seconds.
Exactly. This is a key point about chaos. You also have short-term predictability, but long-term, it's unpredictable. And that unpredictability, it comes not just from the chaos itself, but also from the limits in how precisely we can measure things. Our instruments add some uncertainty too.
It's like the dripping faucet is always forgetting its past. And that forgetting makes it harder to predict the future.
That's a great way to put it, and how fast it forgets, that's what Shaw called entropy. High entropy means lots of information loss and therefore more unpredictability. Now, to try and model this whole dripping process, Shaw used a simple analog model of a mass and a spring.
A mass and a spring. How does that even relate to a dripping faucet?
It might seem weird, but they're actually pretty similar. This mass spring system can do the same dripping patterns, periodic, period doubling, and chaotic.
No way.
Seriously. By adjusting the model's parameters, like the spring stiffness, Shaw could make patterns that looked just like the real faucet data.
So this simple model could still capture how the dripping worked.
Exactly. This means that these patterns, they're not just about dripping faucets. They're probably fundamental features of lots of systems.
So it's like those same math principles are working in both the model and the real faucet.
Right. It shows how powerful models can be for understanding complicated things. But of course, no model is perfect.
So what were some of those imperfections? Where did his model fall short?
Well, one of the biggest challenges was dealing with noise. In the real world, there are always these random fluctuations, and they can make it really hard to see those underlying patterns.
Yeah, it's like trying to listen to someone when there's a ton of background noise going on. Sometimes it's just impossible to hear what they're saying.
Exactly. And noise can be a real pain when you're trying to look at chaotic systems, because even tiny uncertainties can become huge differences over time.
So how do you even deal with that?
Well, Shaw had to get creative. He had to find ways to feature out the noise so he could get to those patterns hiding underneath. You mentioned symbolic dynamics earlier.
Mhm.
That was one of his really clever tricks. Remember how we talked about putting those drop intervals into categories like long and short?
Yeah.
That's basically symbolic dynamics. It's a way to simplify complex data by turning it into a sequence of symbols, like a code.
Okay, so instead of looking at the exact time of each drip, we're just looking at the pattern of long and short intervals.
Right, like you're translating the dripping into Morse code with those dots and dashes.
That's cool. But why even go to all that trouble? What's so great about using symbols?
Well, for one thing, it can make it a lot easier to work with complex data, especially when you're dealing with chaotic systems. By boiling everything down to a few symbols, you can more easily pick out the patterns and figure out how predictable things are.
So it's like a shortcut for understanding the chaos.
Kinda, and what's really wild is that Shaw found that this symbolic approach could uncover hidden structures in the dripping that you wouldn't see just from the raw data. So what did he find when he used this symbolic analysis on his dripping faucet data?
Yeah, what did he learn?
He found that whether he could predict those symbol sequences or not depended on where he drew the line between long and short. You know what I mean? Like
Yeah.
how he decided to split up the data.
Okay.
Sometimes knowing the past symbols meant he could predict the next one pretty well. But other times, the sequences just looked random, no matter how much he searched for patterns.
So how you choose to categorize the data, like how you define those symbols, actually changes how much you can predict about the system.
Yeah, isn't that wild? It shows you that the way we think about a problem, the way we decide to represent information, can totally change how we understand a system. Different approaches can show us different sides of what's going on, which makes you think about everything, right? Like how we learn new things, or just try to make sense of the world.
Right. Maybe there's not just one right way to understand things, but lots of different ways that can teach us something.
Exactly. Shaw's work encourages us to think about all those different viewpoints and to try different ways of representing information. It's a good lesson for scientists, but also for anyone who's curious about the world.
This whole conversation has been incredible. I never would have thought something as simple as a dripping faucet could teach us so much about chaos, information, and how we do science.
It just shows you the power of being curious. By taking the time to really look at even the most ordinary things, we can find some really amazing truths about the world around us.
So to all our listeners out there, next time you hear a dripping faucet, take a second to appreciate all the amazing physics and information that's happening right there in your own house. It might just inspire you to see your everyday world with a bit more wonder.
And remember, you don't need a fancy lab to do science. The mysteries are all around us, just waiting for us to discover them.